and welcome to Instagram. I'm Kamalina and here are my teammates.
Hi, my name is Muhammad Kazmin.
My name is Nur Adliana binti Syamsul.
Hi, I'm Jai.
My name is Muhammad Akmal bin Zaidi.
A diagram is created according to the question. Based on the diagram from distillation column 1, benzene will come out as gas and flow into the condenser to change into liquid. It will then flow into storage tank 3. Xylene will come out from the bottom of distillation column 2 as liquid and will be pumped up to flow into storage tank 2. At the top, toluene will come out as gas and move through the condenser, changing it into liquid to be stored in storage tank 1. The length for the benzene and xylene stream is both 15 meters, whereas for the toluene stream it will be 10 meters. The storage tanks are all placed 3 meters from the ground and their sizes are all set at 6,000 liters for each tank. The distillation column height is set at 8 meters and the height of the storage tanks are set at 2 meters. The condensers were added on the benzene and toluene streams as they will come out as gases and will need to be converted into liquid before we can store them in the storage tanks. Globe valves are used to regulate flow and check valves are used to prevent backflow in each stream. A centrifugal pump is also added to pump the xylene liquid upwards to move into the storage tank. Stainless steel materials is used for the pipes in the diagram.
Next, we have to find the Reynolds number to know the type of flow of the stream. The Reynolds formula is Re equal to rho Vd over mu. There is 4 unknown that we have to find, which is the first one is rho, is density. Since we use toluene as the fluid in this stream, the density of toluene is 867 kg per meter cube. The next one is the V, velocity. As we have calculated before, the velocity of the stream is 37.75 meter per second. D is diameter. The diameter of pipe in the stream that we use is 0.108 meter. And the last one is the mu, which is represented as the dynamic viscosity. For toluene, the dynamic viscosity is 0.00056 kg per meter second. Substitute all of this value into the Reynolds equation, and then we got the Reynolds number is around 6.312 times 10 to the power of 6, which is this value is more than 4,000. Based on the principle, this is a turbulent flow. So since the flow is a turbulent, we can use this equation, this formula, in order to get the friction factor. But we have to find the roughness of the pipe first. The roughness of the pipe, which is denoted as the epsilon, is 2 times 10 to the power of negative 6 because we use the stainless steel pipe in this stream. So substitute this value, the diameter value and the Reynolds number value into this equation, and then we got the friction factor is 0.00249.
Now, we want to calculate the friction loss in pipe number 1. The total friction loss is equal to friction pipe plus friction fitting plus friction valve plus friction expansion and plus friction contraction. Then our formula will be in this form. In the pipe, we have two 90-degree long radius elbow, so our coefficient for fitting is 0.92. For valve, we use globe valve and check valve, so we got 8.3 for our coefficient of valve. The coefficient for expansion will always become 1, and the contraction will be 0.5 as we assume the contraction in the pipe is in a sharp edge form. Then we plug in the value in our formula and we got the total friction loss is equal to 8,295.45 joule per kilo.
To calculate the pressure drop for tank 1, we will need to use the Bernoulli's equation for pipeline system. We know that the difference of velocities is 0 and there is no turbine and pump for tank 1. Therefore, we can simplify the equation into delta P over rho G equals to negative delta Z minus F over G. By putting the values in, we can get a pressure drop of negative 7.217 times 10 to the power of 6 Pascal.
For stream 2, we use the same formula to get the Reynolds number, which is the rho Vd over mu. The fluid is xylene, so the density of xylene is 864 kg per meter cube. The velocity is 63.65 per meter second. The diameter is 0.108 meter, which is same. And the last one is a mu. The dynamic viscosity of the xylene is 0.000812 kg per meter second. Substitute all of this value into the Reynolds equation, then we got the Reynolds number approximately 7.314 times 10 to the power of 6. This value is also more than 4,000, so this is also a turbulent flow. For the friction factor, we use the same formula, which is the flow is also turbulent. The epsilon, the roughness of pipe is also same because this is also stainless steel pipe in this stream. Substitute the roughness of pipe value, the diameter and the Reynolds number, and then we got the friction factor of this stream is around 0.00247.
For pipe number 2, we have to use the same formula to calculate the total friction loss. However, pipe 2 is slightly different than pipe 1 as we have 390-degree elbow. So our fitting coefficient is 1.38. However, the other coefficient value is the same. Now, we plug in the value in our formula and calculate the total friction loss. 25,426.55 joule per kilogram.
To calculate the pressure drop for tank 2, we have to use two formulas which are pressure drop of circular pipe where delta P1 equals to friction factor times length of pipe times density of fluid times the square of velocity over 2 times the diameter. And the second formula is the pressure drop with resistance coefficient where delta P2 equals to the sum of resistance coefficient times density of fluid times square of velocity over 2. By adding both values, we can get the total pressure drop for tank 2, which is 20167321.35 Pascal. Work pump for storage tank 2 can be calculated using the Bernoulli's equation for pipeline system. We can simplify the equation by cancelling the velocity head and turbine head. Therefore, we will get a value of 4974.29 joule per kg. Using the work pump, we can calculate the work pump power using power equals to mass flow rate of spin 5 times work pump over pump efficiency of 90%. The work pump power is 2786.199 kilowatt.
The Reynolds number for this string, we use benzene as the fluid. So to do the same thing, substitute all of this value into the Reynolds equation. And then we got the Reynolds number is around 3.8323 times 10 to the power of 6, which is the value is also more than 4000. So we can say that this is also the turbulent flow. Since the flow is also same, which is turbulent, we use the same formula. Substitute the value of epsilon, the roughness of pipe, the diameter and the Reynolds number of this string, and then we got the friction factor for this string is around 0.00255.
Pipe number 3, we have to repeat the same step as we did in pipe 1 and pipe 2. Since pipe 3 is almost identical with pipe 1, the value of coefficient is also the same. After we plug in the value, the friction loss in pipe 3 is 3616.04 joule per kilogram.
Pressure drop for tank 3 can also be calculated using Bernoulli's equation for pipeline system. First, we need to simplify the equation by cancelling the velocity head, turbine head and pump head. Then we can get the value of pressure drop by putting the values into the simplified equation. The pressure drop for tank 3 is negative 3.195 times 10 to the power of 6 Pascal.
For the justification, the first justification is material of the pipe, which is stainless steel. It is corrosion resistance at the exterior and interior of the tank. It is resistance to abrasive reactions of chemicals and prevent from leaking. The second one is strength and durability. It is extremely difficult to puncture, large force to cause a small dent, and require little to no maintenance. If properly maintained, can work for decades even in high. The second justification is the capacity and size of storage tank. The size chosen are 6,000 liters or 1585 gallons, which are relatively high and suitable to be used in industrial environment. It is to store more chemicals at one time to reduce cost of tanks needed to store. The third justification is centrifugal pump to increase efficiency. The centrifugal pump is suitable for any application that involves low viscosity of the fluid used. It is suitable to transfer large volume of fluid at low viscosity. It have a very simple design compared to other pumps. It doesn't require valves or pistons, and their moving parts are very minimal and have low maintenance. It takes a small amount of space. It offers efficiency up to 90%, which are high to make sure the flow of chemicals remains steady and does not interfere much with the work of the pump. The fourth justification is calculation of fluid flow. In distillation column 1, benzene will come out as gas, and in distillation column 2, toluene will also come out as gas. Since both of the fluids leaving the columns are in a gas state, the gases need to go through a condenser to be converted into liquids. Since the products flow as gases firstly, hence the early parts of the pipe will only contain gas of the fluids before it is converted. Hence, the length of pipe consisting gases can be neglected in calculation of fluid flow. This is because the product coexists in two different states, which is gas and liquid, and it have different density, thus it can't be calculated as one. So in order to calculate, the length of pipe considered will start after the condenser, and the length before the condenser will be neglected.